Welcome to Math 2320, Section 4.7. In this section, we're looking at a particular type of differential equations. They are called the Cauchy-Euler equations. The equations have a particular format, and that is they look like a constant times x squared times y double prime a1x y prime and a constant times y, and if it's non-homogeneous there's a driving function on the right hand side. So essentially we have powers of x in front of each of the derivative terms. So the idea here for the homogeneous situation is to try a solution of the form y equals x to the m. Much the same way, previously we tried solutions of y equals e to the mx. Here we're trying powers of x. So in the second order case, it would look like in the standard format a2x2 y double prime a1x y prime a0y equals 0. For higher order, it would just have an x cubed y double prime or an x to the fifth and y to the fifth derivative. So they have a particular format where this technique can work. Now, much the same way as previously, we have an auxiliary equation. And this equation looks like a2m, m minus 1, a1m plus a0 equals 0. So in our particular problem, I've got a 1 in the front. There is no y prime term, and I have a constant of minus 12 on the end. And so if I fill those pieces of information in to the auxiliary equation, I get m squared minus m minus 12 equals 0, which is factorable, and I get roots of m equals 4 and minus 3. So my homogeneous answer looks like c1x, x to the fourth, plus c2, x to the minus 3. Or if I take care of x to the minus 3, I can put it as 1 over x cubed. So fairly straightforward. Now when we get to question 2, we have x, y double prime minus 2y prime equals 0. Alright, so let's write that down. X, y double prime minus 2y prime equals 0. Now looking at this, you're thinking something's wrong. I thought we were supposed to have an x squared in front of the y double prime term. Something's off. Alright, so when it looks a little off, we go back to basics. We assume a solution of the form y equals x to the m. Now let's see what happens. Y prime, the m would come in the front. I drop the exponent by 1. Y double prime, the m minus 1 comes in the front. I subtract 1 from the exponent and I get m minus 2. Alright, so now let's fill all this into our problem. Here's the x in the front. Here's all of the terms for y double prime. So all of that's y double prime minus 2, and all of these terms are for y prime. If I combine this x with this x to the m minus 2. Exponent here is 1. So 1 added to a minus 2, and I get a x to the m minus 1. Now if you notice, that term is in common to both pieces here. So factor it out, and I'm left with m squared minus m minus 2m is 0. I can combine like terms here, and I get m squared minus 3m equals 0. I can factor out a common m, and I get m times m minus 3 is 0, and so I get m is 0 and 3. So c1 x to the 0 plus c2 x to the 3. X to the 0 is 1, and so I just get this constant. So not too bad. If everything else fails, go back to the basics. Assume your solution of that particular form, plug everything in, see what happens. Alright, in question 3 here, we have x squared y double prime 13x y prime plus 36 equals 0. So this looks just like our particular format, with a equals 1, b is 13, and c is 36. Alright, so we plug all those pieces in. Here's a, here's b, here's c. Simplify, and what happens is we get a repeated root of m equals minus 6. Now, when you have a repeated root, similarly just like previously when we had constant coefficients and a repeated root, what do? Alright, well, my first solution is c1x to the minus 6. My second solution still has the same m1 as before, except now we have an ln of x. Previously we had an x multiplied by our first solution. Now we have an ln. If we needed more of them, so let's say I needed a y3 for some reason, let's say we had a third order, then it would be x to my first solution, and then I'd have an ln of x squared term to preserve linear independence. Right. And in question 4, let's see, we have x squared y double prime 3xy prime equals 0. Alright, so I see my lead coefficient is a 1, a 3, and my y term is missing, so it's 0. So plugging all this in, where I've got a 1 and a 3, I get m squared plus m equals 0. Factor out the common m, and I get answers of 0 and minus 2. And so here is our solution. The other thing now is to apply my initial conditions of y of 1 is 0 and y prime of 1 is 4. Alright, so if I plug in 1 for x, I get c1 plus c2 must equal to 0. Alright, well, what about y prime? Well, taking the derivative here, so taking the derivative of a constant is 0. This is the x to the minus 2, so the minus 2 comes in the front. c2 x to the minus 2 minus 1, so x to the 3. And if I plug in 1, I'm supposed to get 4. So solving for that, I get c2 is minus 2, But when I add it to C1, I'm supposed to get 0, so C1 is 2. So putting all this into my problem, what C1 is, C1 was 2, C2 was minus 2. So my graph is a flipped over, because of the minus 2, 1 over x squared, and it's shifted upward by 2. So if you remember, 1 over x squared is like a volcano here, but it's flipped over, so it's upside down, and then popped up by 1. And that's what's going on here. We have 1 over x squared, a negative 2 over x squared, shifted up by 1. There is no left-hand side because we're solving this for x greater than 0.